On September 14th, 2015, something truly extraordinary happened. Scientists from the Laser Interferometer Gravitational-Wave Observatory, after years of tireless work, achieved something that had previously seemed impossible. And this achievement was not only scientific, it touched our hearts and minds deeply, and it was a cause for laughter and celebration. After all, how could one not be moved to tears and smiles by a discovery that allowed us to see the universe in an entirely new way? Imagine for a moment that we as humans evolved without the ability to see light for thousands of years. We stumbled and navigated in the dark, relying only on our other senses. But then, a bright day arrived, and someone invented a machine capable of showing us light. Gradually, we began to see everything, from what was right in front of our noses to the farthest galaxies. This analogy helps capture the magnitude of LIGO's discovery. But what exactly is this discovery? What are these mysterious gravitational waves, and why are they so important? I'll explain it simply and excitingly. Gravitational waves are one of the most extraordinary predictions of Albert Einstein's theory of general relativity. They are like vibrations in the fabric of space-time caused by massive objects moving through the universe. Think of them as ripples on a pond, but instead of water, they travel through the very structure of space-time, spreading in all directions. Here's the trick. These ripples are extremely subtle. Some of these signals are minuscule, about 1/10 of a thousandth the size of a proton. Yes, you heard that right. They are 10,000 times smaller than a single proton. And yet, these ripples contain incredible information about their origin, when they were generated, the distance they traveled, and what events produced them. It was like searching for a needle in the haystack of the universe. But don't worry, LIGO is here to save us. It is a pair of giant observatories funded by the United States and operated by prestigious institutions like MIT and Caltech. Imagine them as telescopes that capture gravitational waves instead of light. LIGO is an interferometer, an invention that has existed since 1880, and it is extremely sensitive. It measures what happens when light waves from different sources combine, allowing us to detect these incredibly tiny cosmic ripples. But the story gets even better. The scientists who led this tireless search were awarded the Nobel Prize in Phi. Let's take a look at LIGO, the observatory that uses this brilliant idea to discover gravitational waves. LIGO has two observatories, one in Hanford, Washington, and the other in Livingston, Louisiana. And guess why they have two? To triangulate the origin of signals. Of course, each observatory continuously fires a powerful laser into a beam splitter positioned at a 45-degree angle. This laser is so powerful, it can vaporize anything in its path. And they don't want to vaporize the universe, right? The splitter divides the laser beam into two, and each beam travels down a 4-kilometer vacuum tube to a mirror at the end. The light beams play a sort of ping-pong game between this mirror and a recycling mirror at the other end, now traveling a total of 200 kilometers. Remember what we talked about with interferometers? The larger, the better. After doing this about 300 times, the light beams come back together at the beam splitter and head towards an iodine photodetector, a light-sensitive semiconductor. Here's the cool part. If the light beams remain undisturbed, they will be in phase, meaning their frequencies cancel out and no light reaches the photodetector. But if a gravitational wave passes through, the distance each light beam travels will be slightly different, causing them to go out of phase. That's when the photodetector picks up the signal, indicating that a gravitational wave is passing through. But wait, there's more. LIGO is constantly dealing with noise, even from quantum mechanics, which loves to introduce a touch of randomness to photons. To overcome this, LIGO uses super smooth 40-kilogram mirrors suspended by silica threads. Any particles in the path of the light beams are also a problem, so they keep the air in the vacuum chambers at 1/1,000,000th of atmospheric pressure. And quantum mechanics? Oh, that's a problem too, but LIGO deals with it by using an optical cavity that compresses light, turning phase noise into amplitude noise, which the interferometer doesn't detect. In essence, quantum randomness is still there, but it's like hiding the mess in a closet. The goal is to minimize noise and achieve the best possible signal-to-noise ratio. Now, you must be wondering, what did LIGO discover? Well, in 2015, it detected its first signal, named GWW-114. Scientists analyzed the data and found that it occurred due to the merger of two black holes about 1.6 billion light-years away. These black holes, with masses 29 and 36 times,